Good day, everyone. Welcome to this part 2 of the lecture on radiation. In part 1, we have gone through radiation from a small object to the surroundings and also a combination of radiation and convection. In this part, we're going to talk about radiation between two surfaces. In order to solve problems related to radiation between two surfaces, we need to first understand a very important concept, a concept of view factor, F. Okay, let's first focus on this diagram. And we see a thermal radiation emitted from a surface is to all directions. So for example, you can see a solid surface. On this surface, actually the thermal radiation is emitted by every point on this surface, and every point on the surface will emit thermal radiation to all directions. So you can see now it's 2D, but actually it's in 3D, meaning it's like the radiation is it's like a hemisphere, so it's emitted towards all direction from its surface. Now let's move to this left part, the figure here. So there are two surfaces, surface A1 and surface A2. So they are in a different position, so you see the different angles, everything. So let's assume surface 1 has a higher surface temperature as compared to surface 2. So from what we have learned so far, we know the net heat transferred will be from surface 1 to surface 2. But in radiation, in order to determine how much heat, what is the heat transfer rate Q from surface 1 to surface 2, we need to determine because the quantity of Q is determined by their position. So we need to determine how much radiation emitted by surface 1 will actually falls on surface 2. So that's why we need to need to calculate this view factor, F. Okay, on this, there are several scenarios we can look into. So let's see scenario number 1. Scenario number 1 is if A1 and A2 are infinite and parallel, meaning surface 1 and surface 2 are infinitely long, and the surface area is also infinity, and they are parallel, like for example here they are parallel, and if their surface areas are infinity, okay, then we are very sure that all radiation emitted by A1 is absorbed by A2 and vice versa. Let's see scenario number 2, which is more common to us in our daily life, because we know that everything in this world is the surface area is finite, so it's limited. So let's say if A1, A2 are finite, then we can see it's very clear not all the emitted radiation from surface 1 will be absorbed by surface 2, and same goes to surface 2. Not all thermal radiation emitted by surface 2 falls on surface 1, but part of it will be lost to the environment. Okay, we can see from here, right? So from the thermal radiation emitted, so some of it will reach surface 2, but some of them will just lost to the surrounding, lost to the environment. And what are the factors determines how much radiation emitted by a surface will fall on another surface. There are many factors. For example, their dimension. So if the dimension is bigger, of course, more radiation emitted will fall on another surface. Another one is, for example, orientation. So if they are parallel, the quantity of radiation falls on another surface is different as compared to if they are not parallel. So if we if this is an inclined surface, then the quantity of emitted radiation falls on surface 2 will be different as compared to when these two surfaces are parallel. And another example, let's the distance between the two surfaces. If they are closer, if the distance between surface 1 and surface 2 is closer, then we can see more radiation emitted by surface 1 will fall on surface 2. So that's why we need to learn about this concept of view factor F, so that we can calculate how much of the emitted radiation is absorbed, and then the net heat transfer through radiation. Next few slides explain about derivation of governing equation in calculating the view factor. I'm going to skip the detailed explanation. You can just go through them by referring to the textbook. So after going through this derivation process, at the end you will get the governing equation for heat transfer through radiation between surface 1 and surface 2. And from there, we'll be able to come up with this equation on view factor between surface 1 and surface 2, that is F12. By definition, view factor F12 is the fraction of radiation emitted by surface 1 that is intercepted by, or in the common language we say falls on surface 2. Meaning, in short, view factor tells us how much radiation emitted by a surface, let's say surface 1, falls on another surface of interest, that is surface 2. So from the definition, it tells us that the value of view factor, or F12, lies between 0 and 1. So if F12 equals to 0, meaning none of the radiation emitted by surface 1 falls on surface 2. So the opposite is, if F12 equals to 1, it means all radiation, 100% of radiation emitted by surface 1 falls on surface 2. Okay, and now let's go through a few important remarks on view factor. Remark number 1, value of the view factor depends on the geometry and orientation of the two surfaces. So it doesn't depend on, for example, temperature, for example, viscosity. It only depends on geometry and orientation of the two surfaces. And as you can see here, this is the original formula equation for someone if he's interested in determining calculating the value of the view factor. So in order to get F12, so someone need to solve this double integral equation. But luckily, over the years, there are many people they have calculated the view factor under different configurations, and all these values are available in the literatures, meaning some people have done this work for us and they have published their results, and all these value of view factors are available in the literatures. Here in these slides, so two examples are given. So number one is a line parallel rectangle. So you have rectangle 1 and rectangle 2, I and J. So they are parallel to one another. So if you solve this double integral equation, so this is what you will get. So Fij, so in our case F12 equals to the whole thing. So what is x, what is y, what is L? So x is the length, y is the width, L is the distance between the two surfaces. So if you substitute x, y, L, all this into the equation, then you will get this value of Fij or F12. So same goes to this coaxial parallel disc. So if you solve this double integral equation, so this is what you will get, Fij or F12. There are also some researchers, after solving this double integral, they came out with graphs, different graphs, which enable the users to obtain the result, to obtain the value of F12 by doing some simple calculation. Then after that, they can just obtain the value of F12 by referring to the graph. So there are two examples available in your textbook in page 316 and 317. You can refer to these two graphs. I'm going to explain on how to use this graph to obtain the value of F12 for certain geometry. Let's now see the first graph. This first graph is for the radiation between parallel planes, two parallel planes directly opposed to each other. So you can see the graph. For curve 1 to 4, they are for direct radiation between the planes, and there is nothing between the two planes. But for curves 5 to 8, the two planes they are connected by non-conducting but re-radiating walls. So it's like when you see this, the two planes, plane 1 and plane 2. So if there is nothing between them, so what you can refer to either graph, either one of the curve 1 to 4, depends on their geometry. And if there is, so these two planes are connected by radiating walls, meaning there are walls 1, 2, 3, 4 between the two planes, then you need to refer to curves 5 to 8. So here you can see curve 1 to 4 generally they have lower value of F12, but if you add a re-radiating wall between the two planes act as like something like mirror. So any radiation that falls on the re-radiating wall will be reflected back and will reach another plane. So that's why if you see curve 5 to 8, which is for this case with two planes connected by radiating walls. So generally, their value of F12 is higher. Is higher as compared to curve 1 to 4. If the two planes are circle, let's say, are this, so you need to refer to either curve 1 or curve 5. Depends on if there are radiating walls between them. So let's see this example. Let's see the example. So this example is a rectangle. So the length is 3 meter and the width is 1 meter, and the distance between the two planes is 2 meter. So from here, x-axis is the ratio of smaller side or diameter, in this case of course a smaller side, so divided by distance between planes. So for this example, x equals to smaller side, so smaller side is 1 meter divided by distance between the planes, that is 2. So x-axis you need to refer to half, so that is somewhere around here. So need to drag it to curve, let's see, so it's 1 times 3 rectangle, so you should refer to long narrow rectangle, because if category 2 is a 2-1 rectangle, 2-1 rectangle is if the width is 1 meter, then the length should be 2, so it doesn't fall into this category. Curve number 2 is for square, so it's very clear this is not a square, so we only have one choice, that is long narrow rectangle. So since there are no radiating walls between them, so we need to refer to curve number 4. Curve number 4. So I'm sorry because I'm using mouse, so it's quite difficult for me to draw a line, a straight line. So it would be somewhere around here. Okay, then if we drag it to y, so I think the F12 value is something maybe 0.25, something like that. Now let's see if we reduce the distance between the two planes, what will be the effect to the view factor? So if let's say if we halve the distance between the two planes from 2 meter to 1 meter, then your x becomes 1 divided by 1. So meaning here you will start from 1, then drag it to curve number 4. So you will get almost double. The F12 value will be double. So what if we add? Now we add. So after reducing the distance between the two planes, what if we add radiating walls between the two planes? Then the new F12 you need to refer to curve number 8. Instead of 4, now is curve number 8. So the F12 now becomes close to 0.7. Close to 0.7. So you can see the effect of radiating wall addition and effect of reducing the distance between the two planes. Okay, this chart for adjacent perpendicular rectangle is quite self-explanatory, so I think I don't need to explain much. just that one thing you need to take note is as compared to the previous chart, that is for two parallel planes. The condition for the previous chart is the two parallel planes must have the same surface area. That is, A1 and A2 must be the same. But for this chart, A1 and A2 can be different. You can see here A1, A2, they can be different. Just that if A1 and A2 they are the same, then it doesn't matter you want A1 to be here or A1 to be here. It doesn't matter if A1 and A2 are the same. But if A1 and A2 are different, then you need to take note A1 is here. A1 is the area on which heat transfer equation is based on. Okay, you understand more when we go through the following slides. So just bear in mind of this. Okay, now let's continue with remark number 2. That is, a surface has a view factor with respect to itself if it is concave. So what does it mean by view factor with respect to itself? So for example, this is surface number 1. So view factor with respect to itself, it means F11. So normally it's the view factor is with respect to another surface, but for some shape, some types of shape, so that surface has a view factor with respect to itself. So I'll give you 3 examples here. You see the first one, it's a convex surface. A convex surface. So a convex surface, if you see any radiation emitted by the surface, okay, will force on the surrounding. It will not fall on surface 1 itself. Yeah, because of the geometry. So it means you see, so it's going to be emitted to all other direction, to every direction, but none of the emitted radiation will fall back on itself. So when this happens, it means F11 equals to 0, meaning view factor with respect to itself for this kind of surface, for convex surface, equals to 0. So the same principle applicable for a flat surface. You can see here. So a flat surface, the same situation. All the radiation emitted from every particle on a flat surface will be emitted to the surrounding, and none of this radiation will fall back on itself. So that's why the conclusion is F11 for a flat surface also equals to 0. But you see, if you see a concave surface, which you can see from this diagram, some of the radiation, of course, it will be emitted to the surrounding and will not fall on itself. But you can see there are some radiation. I'm sorry, it should be straight. So you can see some of the radiation will fall on itself, will fall on surface 1. So it means it's very clear in this case the F11 does not equal to 0. So meaning a concave surface has a view factor with respect to itself. And this basic knowledge will help you a lot when you try to determine view factor for different surfaces later. Remark number 3 is called summation rule. So according to summation rule, any surface in an enclosure will have a view factor with respect to all other surfaces in the same enclosure. And sometimes it depends on its geometry. Sometimes it will have a view factor with respect to itself, like what we have explained in the previous slide. You can see this example. So this enclosure consists of seven surfaces: 1, 2, 3, 4, 5, 6, 7. So let's take surface 1 as example. So you can see surface 1 has a view factor with respect to all other surfaces, and if it is not a flat surface or a convex surface, then it will also have a view factor with respect to itself. So that's what. And according to summation rule, if you add all these view factor together, it will become 1. So meaning in this case, f11 plus f12 plus f13 plus f14 plus f15 plus f16 plus f17 equals to 1. So this summation rule will also help us when we do calculation for view factor. Remark number 4 is called reciprocal rule. Reciprocal rule gives a relationship between two surfaces in terms of their surface area and view factor. As you can see, this is the general formula of the reciprocal rule. So this reciprocal rule is derived from this equation, that is the net heat transfer between two surfaces. As you can see, Q12 equals to negative Q21. Okay, that is the net heat transfer between two surfaces. So start from here. You can see Q12 equals to F12A1 sigma T1 power 4 minus T2 power 4. So and if as we proceed, so this negative, we'll put it inside. So we change the position of T1 here. Okay, so and sigma cancel out, T1 T2 cancel, T1 power 4 minus T2 power 4 also cancel. So what is left is F12 A1 equals to F21 A2. And if from here A1, if A1 equals to A2, so what we can tell is F12 will be equal to F21. So that is this is a very useful rule which enable us to determine view factor. And now let's see an example how we can apply this reciprocal rule in determining view factor. Let's see the diagram on the left side. So we have two surfaces. Surface 1 is a convex surface. Okay, and surface number 2. So surface number 1 or body number 1 is inside inside of surface number 2. So it's like if you want to visualize, it's a ball inside a box, a closed box. Okay, so from here, we actually know F12, okay, without being taught, from what we have learned in the previous slide, we already know F12 equals to 1. Okay, F12 equals to 1. So, and what about F21? So we can use reciprocal rule to calculate what is F21. So provided this information are given, meaning what is the radius or diameter of surface 1 and what is the length of surface 2. So we assume surface 2 it's a square, okay, it's a cube. Okay, let's see. So according to the reciprocal rule, F12 A1 equals to F21 A2. So if we rearrange the reciprocal rule, what we can get is, we know F21 equals to A1 over A2 times F12. Okay, and what is A1? A1, it's pi R1 square, and A2 is L2 square, and F12 equals to 1. Okay, so from there we know is pi over 2 times 2. 2 times 2 is 4. So F21 equals to pi over 4. So you see how useful is this reciprocal rule. So it enables us to determine some of the if the conditions are met, it enables to determine the view factor. But for case number 2, you see on my right hand side, so because in this case surface 1 is a concave surface, and we don't know what is F12. Okay, so unless one more information is given, that is what is F12. If F12 is given, then the same process we can go through in order to obtain what is F21. And remark number 5 is called superposition rule. So superposition rule states that the view factor from a surface to a composite surface is equal to the sum of the view factors from the surface to the parts of the composite surface. So what does it mean? Let's see the first part of this diagram. So we see surface 1, surface 2 and surface 3, and in this case surface 2 and surface 3 actually belongs to one surface. Okay, it's just that we break it into 2 and 3. So according to superposition rule, in this situation F1 to 2, 3, so that is we see this surface as a composite, as a combined surface, F1, 2, 3 equals to F12 plus F13. Okay, this is the superposition rule. This rule is also useful in helping us to determine view factors. But you need to take note, when we say this is true, the opposite is untrue. That is, we cannot say F21 plus F31 equals to F231. So this is not true. And you will see the whole thing clearer if we apply reciprocal rule plus superposition rule. So in this case, for case number 1, whereby is F123 equals to F12 plus F13. So if we apply reciprocal rule, so it's A1 F23 equals to A1 F12 plus A1 F13. Okay, we need to be careful when we apply this reciprocal rule. So you take note. So when the first is 1, to make sure your A is also 1. So you can see it's consistent. So when A is 1, the first term in the F is also 1. So consistent with this, and it's also consistent with this equation. Okay, another point I want to mention here is while we say this is untrue, meaning F21 plus F31 does not equals to F231, but when we apply reciprocal rule, this is true. That is A2 F21 plus A3 F31 equals to F23 F231. This is true. And when I explain further, you will understand why this is true, this is not true. So if you see this equation, okay, let me erase. Okay, when you see this equation, the first equation, you can actually cancel out the A, because here you can take A1 out and it becomes F12 plus F13. Okay, and this A1 can be cancelled out. So at the end you will get this. You will get F123 equals to F12 plus F13. But the same thing cannot be done here. While this is true, so you cannot take A2 out or A3 out, because A2, A3, they are different. Okay, from here, so you can see, you know the reason why while we say superposition rule, according to superposition rule, F123 equals to F12 plus F13 is true. The opposite, that is F21 plus F13 equals to F231, is not true. Now let's go through an example on how to apply superposition rule in solving a problem. So as you can see here on the left side, there are 3 surfaces: surface 1, surface 2, and surface 3. So surface 2 and surface 3 are actually a composite surface, because they belong to the same surface. Okay, just that one surface is divided into 2 and 3, 2 parts. Okay, so you are required, the question requires you to determine what is the real factor of F21. Okay, so from the graph, okay, which we have discussed previously, this chart enable us to determine F13. So you can determine from the chart, because 1 and 3, they are adjacent to one another. Okay, it also enable us to determine F123, because F123 are also adjacent. Okay, so these two, F13 and F123, can be determined based on this graph, but F21 or F12 cannot be determined using this chart because surface 1 and surface 2 are not adjacent. They are not connected to one another, which doesn't fulfill the requirement of using this chart. So how can we solve this problem? Okay, let's see. Okay, F21 can actually be determined by first determining F12 by using superposition rule. So how it goes about, let's see. So according to superposition rule, so F123 equals to F12 plus F13. And I've explained in the previous slide, F13 and F123 can be determined from this chart. Okay, they can be determined directly from the chart. So by using this superposition rule, okay, we will be able to determine F12. So let's see how can we do that. First, we will determine F13. So let's refer to this chart. So Z, we need to first calculate Z. So Z equals to Z over X. So this formula. So Z over X is 1 over 4, 0.25. And Y will tell us which curve to be referred to. So Y in this case equals to 1 over 4. Okay, 1 over 4. This width is 4, so it's also 0.25. So 0.25 is around here, and curve of 0.25 is not there, but it's around here. Okay, so of course a more accurate way is use interpolation. So whereby you take 1, then after that you take 1, then after that you use interpolation to determine what is F12. Okay, so if you do that, so you will get from the chart F13 is almost equals to 0.25 as well. And what about F123? F123, so Z equals to 2 over 4, that's 0.5, and Y equals to 1 over 4, 0.25. Okay, so based on the graph, you will get F123 equals to 0.73. Okay, and when we substitute F123 here equals to 0.37, sorry, and F13 equals to 0.25, then you will get F12. Okay, F12 equals to F123 minus F13, then it equals to 0.12. So that is how we can get F12, although it cannot be determined directly from this chart. Okay, from previous slide, so we have got, okay, using superposition rule, F12 equals to 0.12, but what we are required to calculate is F21. So there is one more step which enable us to determine F21. That is, now we need to apply reciprocal rule. So we know A1 F12 equals to A2 F21. So substitute, this what we want is F21. So A1 A2 F12 are all available. So substitute all these value into this equation, you will get F21 equals to 0.12 also. Why? The reason is very simple, because A1 equals to A2 in this case. So that is how useful this superposition rule, reciprocal rules in helping us to determine real factors in different situations.